Thank you, Tom. My talk is on the future of wind energy, and I hope I think I'm going to disappoint the perpetual motion people on this one. My background's in mechanical engineering, and I've seen things that work and I've seen things that don't work. I had the pleasure of and the opportunity to start my career at the very beginning of the wind energy industry, before there were wind farms. And I was in graduate school, and we were tinkering with the very early wind turbine designs, and I saw many different ideas fall off the table and converge upon the designs that we have today for reasons that I actually understand. So the first thing I'm going to do is try to attempt to get most of you on a similar way of thinking as me, by giving you some of the terminology for wind energy. Then I'm going to talk about some of the trends and some of the future concepts that I think are going to go forward in wind energy. Some of them are, not that many perpetual motion ideas out there, but there's definitely people working on them, and I encourage them to be successful. So the first thing, and I think most people probably already understand some of this, is a typical wind turbine looks like this. The simplest, the wind turns the blades, which spins a shaft. The shaft goes through a speed-up device called a gearbox, and then goes to a generator where the power is produced. And that comes down the tower, and that's where the energy is collected. If you put many of these together, you have a wind farm. And the wind farms tend to be now the size of conventional sized power plants. Am I blocking you over here? I want to know if I'm standing in a good place. Okay, and I have to do this in an hour too. So, three things, real basic. This is a wind turbine tower. The rotor is what the blades are connected to. It's that system of blades connected to a hub that spins. And the nacelle is the part that's behind that contains the drivetrain. Those are the terminologies. A typical large wind turbine looks like this. So the blades are coming through the shaft. Here's an actual cutaway of a pretty much what it looks like: the main shaft, gearbox, and then generator. This happens to be a Nordex German machine. There's two common configurations that you should know about. So we have upwind machines and downwind machines. And you may not have heard those terms before. Most wind turbines are upwind machines, which means the wind is coming through the rotor before it passes through the tower. And that offers a lot of stability issues, a lot of stability opportunities. The machines are oriented upwind by a yaw control system, which means that the nacelle can position itself and face the wind depending on which way the wind is coming from. There are sensors up there that detect that. Downwind machines face away from the wind, so the wind passes through the tower first and then through the rotor. And those have the advantage because the wind tends to blow the blades away from the tower. So a lot of work goes into keeping upwind machines and the blades that are moving around from hitting the tower as they go. I have 3 rules that we have to follow as we go through this. And this is where a lot of the new ideas fail to do their reality checks. So the first one is swept area. The power of the wind is proportional to the area that's of the rotors, the swept area the rotor makes. The swept area is that circle that, as the blades turn around, it's the amount of wind that's actually it's able to capture. And that's true for horizontal axis machines that make a circle, or vertical axis machines which happen to have a profile that looks more like a rectangle. It's all the same. The power in the wind is proportional to the velocity cubed, which means that as the velocity increases, say the velocity doubles, the power goes up 8 times. So we get a lot of benefit from increased power in the wind, increased speed in the wind rather. So the power goes up the cube of the wind velocity. And the last thing is that of all that wind that's going through, that's a big, the wind is a mass, a mass that's flowing through the atmosphere. And that mass is has energy associated with it. We can only get 59% of the energy that's in that wind stream. That's the maximum we can get. Most modern wind turbines are capturing about 50% of that. So there's not a whole lot of headroom in terms of efficiency that can be gained. And that 59% is called the Betz limit. It's named after a guy named Betz. And it's something that we've never been able to achieve any machines that can exceed that. And it's a proven fact. It's mathematically demonstrated, and I don't have time to tell you about it. And you don't want to know, probably. So when you talk about a power curve for a wind turbine, it looks like this. This is the power that it makes versus the wind speed along this axis. So this is the cubic. This is the energy that's actually available in the wind right here. It's the cubic relationship. A wind turbine can't make that. It has to leave some behind. A good way to think of that is if you completely stop the wind, then no wind would be passing through the rotor. You'd take all the energy out, but there would be no energy made either because the rotor would be, because no wind would be, it's just like a wall that's blocking it. So there has to be some movement of air through the rotor, and that's and 59% is the amount that can be captured. So a wind turbine, when it starts to operate, will generate a cubic curve as it increases, but then it reaches a point where it's no longer economically attractive to continue to go up, and it reaches what's called rated power, and it levels off until it reaches a point where the winds are so strong and so damaging that they reach a place called cutout. So all the energy is produced under this curve here. Normally this is about 50 miles an hour. So that means that most of the time the winds don't exceed that, and it's not really worth operating it. And this is about 12 miles an hour, where the winds are so light there's not enough energy in there to bother with. So it's in between the 12 miles an hour and the 50 miles an hour where we do all the wind energy capture. And there's the relationship of the power and the wind. It's 1/2 times the air density, for those of you who are like scientists and engineers, times the swept area, times the cube of the velocity. We can get 59% of that. So today, this is kind of a historic view of wind energy, the total installed capacity of wind worldwide. And so, and for those of you who may not be able to read all this very quickly, the blue wedge is what happened in the United States. The yellow is what happened in Europe, and the maroon here is the rest of the world. As you can see, Europe is kind of got the biggest share right now. It wasn't always that way. The US really started it. This is when I started my career in Altamont Pass in California. Everybody was coming to California because there were major federal tax incentives that were attractive enough to get everybody in the world to go to California and install wind turbines. And every idea that you could imagine was installed there. Some of them worked, some of them didn't. And at around 1985, those tax credits were canceled, and because there was this impression that people were abusing them, and some of the people were actually taking advantage of the system. But I can tell you that after that first 1,000 megawatts of wind was installed, we learned an awful lot about how to build wind turbines. And right around there, the Europeans went home with all that information, and they started building wind turbines the way they wanted to. And that's really what caused the industry to take off. When that started to take off, then the US industry began growing again. What we have now is kind of a mixture of European and Danish, German wind turbines being installed now in the United States. And the industry's really started to grow. You can see that the United States is now second in the world in terms of installed capacity, but 8th in terms of actual amount of energy that's being contributed by wind power. That's actually what this is. So we lag by, in terms of total percentage of energy consumption. Denmark is at 21% wind, but it's the size of Colorado in terms of its electric grid. So it's, but it's using, there have been times when Denmark has been 100% wind and exporting wind energy to Norway during certain windy periods. Historically important, I always want to do the history because, Tom,
is it possible to get to 100% wind in the country?
It's possible. It's absolutely possible. And hopefully I'll get to some of the ways that it's possible. Because it's not intuitively obvious that you can do that because sometimes the wind doesn't blow, right? So it's going to require integration with the grid and storage. And we will talk about that. The historically important wind turbines. These are historically important because they're really the precursors to the modern electric wind turbine. Smith-Putton was built during World War II, and a megawatt-sized machine in Vermont that self-destructed because they didn't have enough steel to repair it during World War II. And the Gedser machine was the prototype for all the Danish wind turbines that you see today. Three-bladed upwind design. This is a picture of Tehachapi Pass in the 1980s. It's about 30 of these 100 kilowatt V19 Vestas wind turbines on the hill. And as the industry grew, they became a little bit neater about how they did the wind farms. This is what it looks like today. This is, I think, a Texas wind farm. Those are 1.5 megawatt machines. So about 2 of these machines equals all those machines in the previous picture. So today we have a maturing and actually viable land-based utility class technology for wind energy. Most of the machines are now being installed around 1.5 to 2.5 megawatts, and they're in the upwind configuration that I described. So the wind's passing through the rotor first. They're up on towers that are 80 to 100 meters tall. They have these modular designs, which means that there's a gearbox, and then there's a coupling, and then there's a generator. And you can take the gearbox out, and you don't have to remove the generator. There's 3 stages to that gearbox, so the generator's rotating at high speeds. This is just a convenient way of using the types of technologies that are available today. We have full span pitch control on most of the rotors, which has enabled a lot of, basically it's enabled us to get rid of the brakes, the mechanical brakes on the machines. So the blades can operate independently. So one blade is capable of stopping the whole rotor by itself. Just pitch it out of the wind, and it can stop the machine. So you have triple redundancy on the stopping. That's why you don't see machines running away like they used to. We used to have runaways where if the generator quit and the coupling broke, the rotor would just overspeed until it went supersonic and then just exploded. And that happened. I mean, I've seen it happen many times. We don't see that anymore because we have experience and controls, and we respect the power of these things to do that. Plus, they're expensive, and you don't want to do that. No, it's not a good thing to see. 98% availability means the machines are operating 98% of the time. They're available to produce power. That's a testimony to the reliability of the current systems that are out there. 32% capacity factor means the average power that they're producing is 32% of the maximum power that they can produce on average. Some are 50% capacity factors. This is what a typical land-based machine would do. We need to work on some of the O&M still and reliability issues for land-based. So what new technologies of wind turbines, what will they look like? What will bring them about? And what impact will they have on our future energy use? And this is a picture that was taken in UK. It's an actual picture of I can't remember the name of the wind farm. First, I'm going to show you, though, some ideas that I don't think will succeed. And I think we're going to disappoint some people in the room, but I have to show you. And Tom sent me this first idea by email and asked me to comment on it. So I read the ad here. It's the maglev wind turbine. It says it can power 750,000 homes. And we were having a debate whether this was a Chinese homes or American homes in typical. But I did some calculations on that. And in order for this to be true, at least in the United States, it would have to be 3 kilometers high, which is 7 times taller than the largest building on Earth. And so they're making these claims, and I just, each time I look at something like this, sometimes it's easy to see that it can't be true. There's a few other things that you wouldn't do. You wouldn't put so many blades on a machine because they don't pay for themselves. They actually cause drag and would block the wind more than they would let it through. So that would just be an expensive way to do a vertical axis machine. And the best thing about it, I think, is this magnetic levitation bearing that they propose to put at the bottom, which means there would be very little friction to the whole system. There's another idea that, at first glance it says, yeah, if you can get wind aloft, why not go even higher and get wind out of the jet stream, because the jet stream's like 200 miles an hour, right? So they propose these. There's several companies that want to do this right now, but we've looked at this, and when you do the math on the cable, that really kills it. The thrust load on a 5 megawatt wind turbine is about 250,000 pounds. So that means this cable has to be capable of holding a half a million pounds thrust and still be light enough to stay up there. And it just won't pay for itself. And when you get to the FAA regulations, they've already rejected any proposals to even test a prototype on this, because this basically amounts to a slalom course for 747s. And I think that will end it. I really do, unless they stop having airplanes, which could be part of the future too. I don't know what this is. I found this on the internet. It doesn't seem to make any sense. But I think they were actually thinking that if they put a cowling around the tower, that they could prevent birds from going through the rotor. And it turns out that birds aren't really as big a problem as some people make them out to be, bird and avian impacts. So we can talk about that. I don't have a big presentation on it, but if you have questions about that, I can answer it later. Here's another one I thought was kind of interesting. An offshore wind farm, but there's like a whole village here in the middle of it. But the problem is that these wind turbines are too close together, and the winds that would go through there would be interfered with by the turbines themselves. So it's an interesting idea. So I want to talk about more, let's start from today and see where, answer some of the basic questions here. This is drawing circles that represent the size of wind turbines as we've grown since the 1980s. So this is to show you that really the size of wind turbines has increased dramatically since the industry started, and it will continue to grow. This is the last circle is really the size of the average offshore wind turbine that's being built today. And those numbers below, this is the swept area of the circle in terms of what it would take to generate that amount of power, and proportionally these circles are about right. These are acres. So this is so a 5 megawatt turbine is consuming a stream of that's a 3 acre circle of wind. And that's why wind turbines work, because they really can capture a huge amount of a big, huge river of wind coming at them. But there's a lot of wind, and that's the good news. So in the future, where will they go? There are several companies right now that are looking and building 8 megawatt machines. So they're growing incrementally. And are we going to see a big jump? Are we going to see something go to, when will it stop? How far will that go? The Europeans are talking about 20 megawatt machines right now. And to do this, it's going to take a lot of technology. Difference is we've kind of reached, at 5 megawatts, we've reached some technology limits. And every time we reach technology limits, I say, well, that's as big as they can get. But then they always get bigger, so I don't say that anymore. And but here are some of the I call them enabling technologies. These are things that we're going to need to work on to overcome these size limits of 5 megawatts and go to 8, 10, 20 megawatt machines. And in a minute I'll explain why we might want to do that. Lightweight materials, stiffer, stronger materials. high-speed drives. And I want to add to that lightweight drives because we're looking at superconducting generators right now. Superconducting generators are, 20 years ago they were kind of science fiction, but they've actually built some generators that work in, or at least motors that work in ships at 36 megawatts. So full scale, that's kind of the size we want to get into. They're a third the weight of a classic direct drive generator. So these are something we want to look at because as weight goes up, as size goes up, weight is going to increase with the cube of the length of one of the blades. And power only increases with the square of the blades. So the machines are going to get heavier the bigger they get. That's why King Kong is really just a cartoon character, because really big gorillas don't exist because their weight would be, they couldn't walk around like they do, like King Kong does at least. And whales survive because they're in water. But basically there are limits to scaling. Through technology we've been able to overcome those limits to scaling by continually getting into these lighter, stiffer, stronger, better materials. Can I get a question?
Why don't you put the generator at ground level? What's the reasoning behind that?
Because you need a shaft that will go down 100 meters. That would be the main reason. And they did do that in some of the earlier designs, but that shaft is heavy if you do the math on that. It would be a lot heavier than the benefit that you get. And that's really the reason. So we've got a lot of work here. The reason we want bigger machines is because the machine costs about, on a land-based system, the machine's about half the cost of a project. The other half is the installation, the operations and maintenance, the balance of station costs, the grid and infrastructure. And all of that stuff gets cheaper as the machines get bigger. So we're willing to let machines grow and get a little bit more expensive. Actually, we've been able to maintain the cost. But as the machines get bigger, the cost of the whole project has been going down and down. It's made the economics better and better as we go. It's just a lot easier to maintain one machine than 30 machines of the smaller size. So we're looking at drivetrains. Some of the problems we've had with gearboxes. Gearboxes are plaguing the industry right now with some of the failures. The gearbox industry it used to be, the story was, well, we don't have to worry about gear technology because that's a mature industry. We don't have to deal with that ever again because they'll just tell us what to do. About 10 years into the industry, after the lawsuits ended and everybody kind of settled down, we got together with the gear industry and we started implementing their practices and developing gear standards that were right up to the highest level that the gear industry had. And we still had failures. So now the gear industry is working with us, and wind technology is leading the development of the gear industry right now, and we're working to find out what the next technology of gears needs to be in order to solve this problem so we can get to gearboxes that will actually last for 20 years. And the number of hours they have to operate in a wind turbine is phenomenal. Over 100,000 hours. So it's a big challenge. So we're looking at other things too. So that's why we have direct drive generators and other types of gearing to go with. I don't have a lot of time to go into each and every one of those things. Advanced rotors, we're looking at materials, as I said. One of the challenges for bigger machines is to get materials that are lightweight and stiffer so that we can flip the machine and go downwind so that we don't have to worry about the blades hitting the towers. And that may be the next step to the big machines is we turn the machines downwind. Does anyone know why we don't have downwind machines right now? It seems like an obvious thing to do. Has anyone ever heard that story? When the blades are downwind, the wind passes through the tower and creates a vortex. And the blades, as they spin around, go through that vortex and create this thump. And it's an infrasonic noise below the threshold of hearing. And when you're standing next to a big machine that's operating like that, you can feel your whole chest resonating, and you don't even know what's causing it. It's inside houses where they had machines like this. The dishes were rattling on the walls, and they didn't know what was causing it, and it was a problem. And so we didn't, rather than try to solve the problem with infrasonic noise, we just avoided it completely. And all machines have been upwind ever since, and that's been for about 20 years. So that doesn't mean we couldn't do it, especially for machines that are offshore. We're looking at power conversion technology trends. High voltages will mean we can transmit a lot more power with a lot less copper. And we've got some devices. We're looking at silicon carbide for one. But we need to increase the reliability of these components too. It's probably the biggest thing that fails. It's not the most expensive thing, but when you have to go out and fix it, it's a nuisance. Grid integration is probably the hottest topic today. I don't know if it's going to be the hottest topic in the future, but I suspect that it will be, because we've been talking about this. We talked, in fact, some of the ideas mentioned smart grids. We have to get, the grid was invented for fossil fuels, not the other way around. It was first they had fossil fuel plants, they had centralized power stations, then they invented the grid to transmit the energy around the country. Some people consider that to be one of the greatest inventions of human beings, but it wasn't designed for remote power, and it wasn't where wind turbines tend to be in remote areas, and it wasn't designed for power sources that were intermittent, that couldn't be controlled by the operators. So we need to reinvent the grid. And we're in the process of doing that, but the people who run the grid it's pretty entrenched industry, and they have a certain way of doing things, and that whole way of doing things has to change. Here the graph shows what some aggregation of, this is wind plant output, and it demonstrates the variability that you might see from a wind plant. So we have to learn how to fill in the gaps in between the dips that happen in between, and we're doing that right now. We have a lot of work going on with the grid itself. Fault tolerance is a big thing. Capability to ride through faults as they happen. They used to say, take those wind turbines off the grid so we can deal with that problem. Now they want it to stay, the wind turbines to stay on, because they create more stability for the grid. VAR control is capacitors, providing reactive power to the grid while the wind turbines operating is just a benefit all around. And now what we're talking about is high penetration grid studies that get us to 20% and beyond. And by penetration, I mean that the wind is contributing at least 20% to the total electricity that's coming in. And that's where we're going in the next 25 years. And beyond that, we can go even further, because we're not resource limited. Wind can generate beyond the 20%. And the big issues are in the grid. How to redesign that grid to be able to handle the variable power sources that are in there. Do you have a question?
Actually, just thinking, when you have do you have wind resources available? I mean, I know like the whole plain states have a lot of wind, but if you think about the Northeast, do you have enough wind resources to make that part of the grid independent, or is it going to be dependent on the area?
That's a big part of it, and I actually have some slides on that. And the answer is yes, and that's a big part of the problem. So you're starting to see that there. I mean, it's not just if it were just Colorado, would be done. Because Colorado is the ideal state for wind. It's got plenty of open, windy area, and the people are concentrated in one area. You can bring the power in. It's very amenable to what I'm saying, and the problems are not that hard. Forecasting is the other thing here. Whoops, I'm going to go back here. So we're going to have to build new transmission lines. We're going to have to upgrade the transmission lines. We're going to need new policies. Regional integration, I have a whole list here. Transmission planning, these are things we're all working on. 100-meter wind resource maps, we're finding that there's wind in places we didn't know there were. So we have, this is part of our planning, looking at additional power lines that are going to have to be built. So yes, we can bring wind in from windy areas. We can bring wind electric in from windy areas to places where it's not windy, like the East Coast. The wind mapping that I mentioned, here's an example of Indiana. Everybody thought 10 years ago, everybody thought Indiana didn't have any wind because all we had was this 50-meter map of what the wind resource looked like. And if you look at these, the colors here, like the purple bars, purple's really good. And the orange is, it's okay, and the yellow is starting to not so good. When we went up to 100 meters, we realized that we had really good winds, but it's because there's wind shear in the boundary layer of the atmosphere. And so no one really went up that high to check it out, but when we did, we found that the whole northern part of Indiana is a good wind state as long as you can build a tower that's 100 meters tall, which is well within the capability of the technology today. But here's what I've been working on. It's offshore technology. The status today is that it's all in Europe. There's nothing going on in the United States except for there are several projects planned. The machines are bigger because we're not constrained by transmission. The parts for machines get so big that you can't ship them over highways and you can't lift them with conventional cranes. So offshore, that's not the problem because the cranes are bigger and we can barge everything everywhere. The towers are going to be shorter because there's no wind shear offshore. That's the bad news for that, but at least you don't have to reach up so high to get it. There's tons of wind offshore. We have a lot of technology in oil and gas that will benefit. We can transition right from oil and gas into this type of technology. The construction industry offshore will thrive on this. The capacity factors are much better offshore. We can get 40, 50% versus 35 on land. But these are in the early technology development stages. In Europe, most of the wind farms are in the North Sea. Recognize the shapes of these countries. The red stars are the actual wind farms that have been installed. There's about 20 of them already. But they're thinking differently than the United States is. The US is almost totally focused on this lucrative land-based resource that we're developing right now. But when they start hitting transmission barriers, we may want to start thinking about offshore sooner than later. In Europe, they're thinking about it now. These are their goals. The EU targets show they want to do 5,000 megawatts by 2010, and that's just the beginning. They want to get up to 150,000 megawatts of offshore wind by the year 2030. These are goals that they've set, and these are just. This is the planning horizon. This is not the end of the day. You know, in 2030, they're not going to stop putting in wind farms. So this is a big opportunity for offshore wind. And right now, most of this technology is being installed in shallow water, which means they're putting monopiles in the sand. It's not there's nothing that tricky about it, but the machines are bigger. So what's at stake in the United States? And this actually goes to what you were asking me about. 78% of the electricity in this country gets used in coastal states. And those coastal states aren't the windiest states on land. The terrestrial wind is pretty low, actually, when you go right ashore. But offshore, you're talking about class 6 winds, which are really good, the purple. That's the good winds. And they're there everywhere. And mostly in the northern latitudes, more so than the southern latitudes. So it's a big opportunity for wind energy to look at both the coastal and offshore wind resources and the wind resources in the interior of the country. And we're going to have to do it. So let me just look at resources now. This is land-based. This is what I'm trying to say about the resource. The dark states, the dark green, means that in that state, there's at least 100% of the electricity that state uses could be generated from wind energy. In some states, and I just did this as roughly, in North Dakota, it's like 800 times more. You know, I think North Dakota can generate half theoretically, it could generate half the electricity in the country. You know, Texas is a big state. It uses a lot of energy, but it could easily generate all of its electricity with wind. And so you can see where the wind belt is in the center of the country. There's a few places like that in the Northeast, but not so much. You know, in some of these other big states, like California has a lot of wind resource, but it's also got a lot of people. So there's this is just looking at land-based. So now if I look at the shallow water offshore, and look at it that way, there's quite a few more states get added. Unfortunately, I don't have a graph, a map that shows both together. But quite a few East Coast states come to play now with just the shallow water resource. Now, what if we didn't have to put the wind turbines and fix them to the bottom? What if we could float them into the ocean? And that's really the next level of offshore wind, and this is what this map shows. Deep water floating wind turbine systems. And if you do that, then pretty much every coastal state, including the Great Lakes, plays, except for Louisiana, Alabama, the southern Gulf states, and that's just unfortunate geographic location because they don't have the winds except for the ones that you don't want. And so the resource is there. We're not resource constrained. And there are several projects that are being proposed in the United States today. You see there's about 10. And I don't have this completely up to date, but most of the big projects that are being proposed are up in the Northeast, where the people happen to be, which is the big benefit of offshore wind. Most of the population is within just a few miles of where these good sites are. So the transmission problem is not an issue compared to some of the other issues that we have to deal with. So when you're comparing bringing power in from Colorado to New York, you should be thinking also about putting wind turbines off of Long Island, because that's a lot easier, actually. So the technology for offshore is going to play out like this, I believe. We've done quite a few studies on the resource and looked at the bathymetry, which is the depth, compared to the wind resource that's over that area, and come up with some rough numbers. But today, the current technology looks like this. It's a monopile. It's pounded into the sand. The depths don't exceed 25 meters yet, and that's what we call shallow. If you go beyond that, you need something different. You need a foundation that's got like a tripod or a broader base. It's not so exotic, though. It's something that the oil and gas industry uses regularly. It's just a matter of getting the cost down of the equipment to install it and the fabrication of the system. But basically, as these machines go out like this, they'll get bigger. We've calculated the resource for these, and that's what's down here. So there's 430 gigawatts of potential for shallow water. We haven't filtered out the exclusions that are necessary for, say, putting them near military bases or in navigation channels. This is just raw numbers. Does anyone know how much the national grid is? That's about half the national grid for a resource. But if you add in the transitional depths, which is 30 to 60 meters, you've got a number that, if you add those two together, it's almost equal to what the national grid is. And then if you add floating, you're up to another 1,500 gigawatts of potential. And so if you add all those together, the offshore resource is very large. It's not as big as the land-based resource, but it's big enough to do a large amount of our energy production.
Yeah, Technology Review had an article last week about the development of floating offshore wind turbines, and so it looks like they're in the process of testing those out. Do you have any information on that? Or it seems like it's in an experimental stage right now.
Yeah, to be honest, there's only one company that's deployed one in real life, and they haven't actually generated any. I have a slide on that stuff, so later. But I believe it's the end game for wind energy, floating wind turbines. The nice thing about floating wind turbines is that you can avoid all the issues with visual impacts that people bring up all the time with respect to putting wind turbines on the horizon, because you can get further out. Here's a nice picture of Horns Rev. This is a Danish wind farm that's about 7 to 10 miles off the coast of Jutland in western Denmark. It's arranged as 80 turbines arranged in an array of spacing 7 rotor diameters apart. So they're evenly spaced into an array, and I can't tell you which way the wind comes from. This wind farm generates 160 megawatts of power. where it's rated at 160 megawatts of power. And it's a typical, this is the prototype for the future wind farms of Europe. The new ones that are going in will be bigger.
Is that
Yes, sir.
the 7 rotor lengths apart? Is that a kind of a standard number?
We're still working out the number. I don't think that will be standard in the future. I think it will, it's, on land, typically they put the rows, they'll arrange them so that the wind turbines face the prevailing wind direction, and the rows are further apart than the spacing in between individual turbines. But if there's no prevailing wind, if the wind comes from everywhere all the time, then you have to kind of it has to be more amorphous and spread out. But they found all kinds of effects that they didn't intend on this. One interesting thing is if the wind is coming from the corner like this, and this is like a chevron, and maybe like a flock of geese flying. And they found that these turbines outproduce what they would make if there was just one turbine sitting there by itself. So they're finding that there may be arrangements that can actually enhance the amount of energy that a wind farm can make. The bad news is if, in the same condition, these turbines back here they're doing really poorly in the back of the wind farm, because there's all this mechanically generated turbulence that comes through, and it disrupts the power production. So we're not done with array effects. We're just beginning, in fact.
What's the big advantage of rotors rather than vertical fins?
Vertical axis, or like the egg beater type designs that you've
Like
seen.
the one that they showed at the magnet. Right? You never see those, or rarely see those compared to these. A horizontal axis rotor can scale to very large sizes without gaining a lot of weight. A Darius type machine or a vertical axis gets heavy faster. There's another reason. The winds are, as I mentioned in Indiana, the winds are stronger the further up you go. So, and remember, the power is proportional to the cube of the wind speed. So if you get a couple more miles per hour, you make a lot more energy. So there's a lot of economic benefit to reaching up high. And the vertical axis machines can't do that. A lot of their blade length is right near ground level. So they tend to not make as much energy. There's a little bit of an advantage to the power production that a horizontal axis can make, but not enough to make it go off the table completely. It's those other reasons that have killed it, at least for now.
I mean, I've seen planes with propellers that are right
Counter-rotating?
They're counter-rotating.
Yeah.
To improve power. With putting a secondary blade on that same pylon, would there be any advantage? Has there been any testing on that?
No, you get diminishing returns very quickly from extra blades. And you see the American farm wind turbines or windmills they look like a fan, like you can't even see through them. It's just solid, a solid blade. Those are high torque machines, but they can't generate a lot of power. There's too many blades. The blades actually get.
A secondary set of blades. 2 sets.
Oh, 2 sets, yeah. There was some work done on that by some of my colleagues a while back, and I can't say that they showed enough improvement to make it worth it. The problem with that is you're already at the most you can get. Say that there's a tube of air. The most you can get is 59% of the energy going through there. If you put one right behind it, the most you can get. Say you're throwing. Yeah, I mean you can't really get any more than what's. It would be better to put the second rotor next to it instead of behind it. You know what I mean?
Some time ago, there was a technology put out in hydraulics for boats. Volvo put it out. It was called a dual prop, where one prop would go this way and the other prop would go that way, and they would cancel each other out in terms of vibration and actually
and torque.
give you almost twice as much power. Is that possible with wind turbine technology?
Well, I think it's the same question, really. I think it's possible, but it's not going to give you twice as much, because it's different when you're trying to generate propulsion, because you
you can add more energy, and you're not concerned about how much energy you put in. If your objective is to create speed, and you've got a very dense liquid like water, then it's a different problem. But there's only so much energy in the wind before you stop it, and the best way to get it is this horizontal axis machine. And you can, all these ideas about putting cowlings and things around the machine, they just don't pay for themselves, because all you have to do is add, another meter to the blade, and you've increased your swept area by an awful lot as you go out, and that's not very expensive to do. I'm going to keep going onto transitional depth foundations, which means just deeper water. We've got they're starting to look at this, because as we go through the shallow water, we're going to use up those sites more quickly, because they're closer to shore, and there's more sensitivities with the environment and with impacts on people. There's one project that's gone in already. This is a 5 megawatt machine, biggest machine actually installed in the world. It's out in the Beatrice Fields off of Aberdeen, Scotland. There's 2 of these machines. This went in last year. Here's the blade that goes on that. That's a tractor trailer. It weighs about about 30,000 pounds, roughly. Yeah, and it's got a substantial amount of carbon in it, because you have to stiffen blades like this so that because this is still an upwind machine, so you're trying to put enough stiffening into the blade so that it doesn't curl back and hit the tower. That's what the big game is on upwind machines now. 45 meters water depth. So the next step is floating wind turbines. We've just started to look at this. We're trying to explore different platforms that they should go on. Should it be a barge, which is buoyancy stabilized? Should it be a tension leg platform, which is mooring line stabilized? You take a big tank and you suck it down into the ocean. And as long as these lines don't go slack, you get a very stable structure. Here you've got a spar, which is ballast stabilized. So you put a lot of weight down here and buoyancy above. And the waves are happening up here, so this thing just stays put. And it doesn't really want to move around very much. I don't know which one's going to win, because we just started looking at this. We just started developing the computer models that can couple the hydrodynamics to the aerodynamics of a wind turbine.
How deep is it?
The spar has to be the deepest, about 100 meters depth. These, I think, need to be about 60 meters to make them. And I think a barge could go in shallower water, but our modeling of the barge looks the worst so far, because it's right in the wave action, and it tends to move with the waves. And I don't think we're completely done yet, but I have the least confidence in that. One of my professors drew this picture in 1973. He envisioned a wind ship. This is you have to get into the mind of Bill Hieronymus back in 1973, because wind turbines hadn't even been developed yet. And he was thinking about floating wind turbines, and he envisioned that these machines would make hydrogen and fill these tanks with hydrogen. He was a sub-commander in the Navy, so he spent a lot of time thinking about this. And we used to laugh at him, and now here I am. So now, and actually, this is his concept. I think we're not that far from it. I think we've done the hard part, actually. The next step is to couple the wind turbine with the floating system, which is the oil and gas industry's specialty right now. Here's an example of our barge. We modeled this. This represents one guy's PhD. Okay. So these are actually fairly high seas, but what we're trying to do here is understand the dynamics of the system in a wave environment. And obviously, wind turbines don't have to do this on land. So the question is, what do we have to do different to a wind turbine that's on a floating platform? And personally, I just think this amount of hydrodynamic motion is too much. We could make the barge bigger, but I think we're ready to try a spar or a floating or a tension leg platform. And this is a good reason why you should do your engineering homework before you go out and spend like $5 million on a test turbine, which some of my colleagues have done or are doing right now. And we're back. So this is a machine that was built by, or actually it wasn't built yet. I think they're actually in the process of building it. Norsk Hydro is an oil company in Norway that's working on this machine right now. And this is a spar-type design. So they have this big long tube. It's designed to go in very deep water. This is a 5 megawatt type machine. I think this is a technology that we're going to see a lot of. They haven't deployed it yet, but they do plan to put their first one in the water next year. There's a company named Blue H Technologies. If anybody has followed the controversy around Cape Wind in Massachusetts, this is a company that has been promoted by the opposition to Cape Wind, actually. And this is not their doing, this is the opposition to Cape Wind's doing. Cape Wind is a wind farm that's trying to go forward in Nantucket Sound, where a lot of people are objecting to the possibility of aesthetic impacts that the wind farm would create. So the opposition wants to see floating wind turbines instead go further out to sea where no one will see them, and this is their alternative. Unfortunately, this is the only wind turbine that's ever been even placed upon a floating platform. These guys took it out off of the coast of Italy last fall and floated it for a couple weeks, but it's nowhere near the maturity that would be necessary to generate large quantities of energy. And frankly, this is going to take a lot of capital to mature this. So far, at least in this country, the effort hasn't been made yet. But I think this is just the first step on a long road. So we have a new vision for wind energy. This is something that's actually we're working on. And the vision is that we're going to make 20% of our electricity in the next by 2030. That means we have to increase our supply of wind energy to the electric grid by 20 times what it is today, which I think is a goal that's eminently achievable. And even our president has made this comment in one of the State of the Union addresses that we will supply up to 20% of the electricity consumption of the United States with wind energy, and it's in the Advanced Energy Initiative that the administration put out. So we took him seriously, and we've been working on a plan to do that. The 20% from electricity means this. We're here right now. We're going to increase this blue wedge. The offshore component is the maroon wedge, and that comes on to about 54,000 megawatts, which is a lot of wind. So you can see that the total is about 300 megawatts of wind. That's enough power to supply, probably, I'm making this up, but I think it's about the grid of England, UK, all of UK, and Canada probably to combine. So it's a significant amount of energy. And that is our goal. We're working on what the logistics have to be to get there right now. In order to do that, we need to increase our manufacturing and our installed capacity. We need to start ramping it up right now. So the cumulative capacity would be the blue line, but this is how much we want to put in each year going over to this way. So last year we put in 2007. Last year we put in. Actually, this is old because we were supposed to put in 4 gigawatts of offshore not offshore of land-based wind. We actually put in 5, so we're ahead of schedule, and hopefully that will continue. But in order to achieve this kind of annual capacity installations, we're going to need to ramp up a lot of our industries, and that's good for the economy. We have. This is a prediction of what kind of jobs would be created under this kind of a scenario. About 170,000 new jobs to the economy. These are high-paying jobs, operations, construction, manufacturing, in places where they need jobs too. And we have a whole talk on that, I'll tell you later. I think high-penetration wind power is probably the next step beyond that, and this is where we need to go. 20% is great. We can get there without doing anything really crazy to the grid or without to the environment. We just need to manage the grid better and create deal with the variability by working with the grid operators to deal with those fluctuations. But when we get to higher penetration scenarios, and I'm talking about going to 50% wind possibility, at least in some regions, we can get there easily. And not just electricity, but going transmitting the electricity over to the other parts of the energy use sectors like transportation and buildings. We need to have other ways of storing this wind energy and dealing with the variability. And one of the, and probably a lot of you know this if you've thought about it, if you've thought about the future, the advanced battery technologies that are out there today mean that if everyone goes out and buys a car and it happens to have a battery in it, and it sits in your driveway for 23 hours a day, that battery is not being used for anything. We will, in the next, I think, every 12 years, the transportation infrastructure changes over because that's how long it takes to wear out a car. We will eventually create the storage that's necessary to enable all renewable energy to happen on a large scale. Because the size of the battery that will be collectively owned by the United States and by the general public will be 3 or 4 times the national utility grid. And we will be able to use those batteries through plug-in hybrid electric vehicles to offset the variability of renewable energy. And I think that's really where this is all going to go. And it will happen without us having to spend any extra money on storage. And I'm going to have to finish up, but here are some of my predictions for the future. 20%, we're going to get that easy in the next 25 years, I think. The high penetration of wind is going to be made possible through these firming technologies in the next 50 years through vehicle-to-grid type solutions. We have a natural evolution of these that's going to just happen because that's where vehicles are going, I think. So we'll be able to start to supply the transportation sector soon, I think probably in the next 12 years. Offshore is going to play big in populated areas because it has to. I think that's where the wind resource is. So I think we're going to start seeing the shallow water deployments in this country by 2015. We're going to start seeing Europe go nuts on offshore in the next 5 years. Floating offshore turbines are going to enable the expanded service. It's just a bigger resource area and less controversy because they'll be further from the areas where people are affected. And then finally, I think we're going to see a lot more in terms of hydrogen production that will enable this transportation sector and fuel cells to take off as well. So there's not going to be one silver bullet solution here. We're going to look at a lot of different things. I'm just looking at the wind energy part right now. And if you asked me the question about 2100, it would be a lot of different things. We're going to have energy efficient homes. We're going to have light bulbs that don't use a lot of power because LEDs are going to become mature, and we're going to, when you turn on the lights, it won't use very much energy. We'll have homes that don't require the kinds of heating loads that we currently have today, and perpetual motion too. So I think that's it. Thanks.